Stop.
That was a very short countdown.
Go
You never say 3, 2, 1.
Yeah, I did.
5,
Go over
4.
there. Well, they're not looking.
I didn't see
I
that.
am.
Look who's looking.
Over here.
Oh,
Over here.
because my dad.
All right. Give me that ball. Projectile motion. So notice slow motion as it's going through the air. All right. Does it look like a line? What is it?
It's a
More like
parabola.
Okay, like an arc. Okay. Mathematically, what would we say that looks like? A parabola. Yeah. What if you throw it really, really fast upward? All right. Is it going to be a line?
No.
No. No.
Wait, are you talking position versus?
Like.
No, yeah, position. I mean, yeah, just position. Like if we were to trace it. It would be, yeah, it'd be steeper, and maybe in a relatively very short spot, it might look like a line, but if we zoomed out and looked at it over time, even if you shot a bullet out of a gun, okay, it's still going to reach a highest point, right, and then it's going to start falling down. Would you all agree with that? Okay. So, projectile motion, the most basic form of it looks like you shoot something off like that and it goes up, and then kind of comes back down like that. But there are other situations in which you have projectile motion, okay? What about if it's moving up and down? Projectile motion?
No.
No, really. We have a different name for that. Free fall. Yeah, that's free fall, okay? What did we remember about free fall from last time?
The only force is undergoing gravity.
Yeah, there's only force that it's ever the only force that it's ever experiencing is gravity. Okay, there's no other forces on it. And as you guys were saying, hidden information, it's always accelerating at 9.8 meters per second squared downward. Even though the velocity is initially positive, 0, and then negative, I mean the acceleration is always pointing downward. So yeah, free fall, not so much. We wouldn't call that projectile motion. But what if we had a cliff? All right? And the ball is about to roll off the cliff. Okay? And then so it's rolling, okay? It's not just drop, but it rolls off the cliff. Okay? Notice it will have, as it's rolling, it's going to have a little bit of horizontal velocity, but it's also going to have vertical velocity. So it's not just in free fall. We would say that is in projectile motion. See if I can show it to you here. Did y'all see that? Okay, do we need to do it again?
Yeah.
You are. You say yes even if I slip. All right. So here we go. So even if it's...
Okay, do it again.
No, too bad, so sad, you missed it. Okay, so another example of projectile motion would be, let's say you've got a cliff and something rolls off with an initial velocity that's kind of in that direction, it would still fall and its motion would look something kind of like that. These are different scenarios in which we have projectile motion. We'll assume that in that first situation that the ball is thrown and caught at the same height. Here we would say the ball has a horizontal initial velocity. There's its initial velocity, but then it lands much lower. There are other situations for projectile motion. Can anybody think of another situation? If you throw it down.
Oh, I'm not down.
Okay, so if I just throw it straight down, and you're saying no, not if you go straight down. Throw it, give me some words. Throw it diagonally. Okay, so we're up on the top of the cliff again here, okay? We're not going to jump, but we're going to throw the ball downward like that. Okay? As soon as I release it, is the ball going to do this?
Yes.
No.
Why not, Anton?
I mean, because you have
I'm not throwing it straight down, I'm throwing it kind of like...
horizontal acceleration.
Yeah, there's a horizontal...
Acceleration.
Not acceleration, but velocity. Right. When I release it, I've got a little bit of horizontal velocity, and a little bit, or maybe a lot of bit, of vertical velocity. So the ball is not going to travel straight downward. It's going to travel downward, but it's also going to continue kind of moving off like this. So the ball will actually kind of look, the trajectory would look kind of something like that. Y'all see how it still continues to move, okay? The interesting thing is, if at the same, you could have a ball that was rolling, maybe my head, it rolls off this way, okay? That will also, like we saw, have a parabola. It's probably going to go farther because I'm not throwing it down at all, okay? So if I were to have a ball that I threw downward, it's going to have a horizontal part of it, but it's going to vertically, I'm adding some velocity, so it's going to go down faster than a ball that just sort of rolls off sideways. Yes?
At what point when you say throw a ball or it rolls off, would it stop having more horizontal velocity and start becoming more vertical? Because it goes down like this, it doesn't just go down in a slant if you throw it diagonally.
Right, it kind of goes down like this. Well, the good question.
When gravity outweighs the force that it was thrown with?
Well, here's the thing. Gravity only affects its vertical velocity. Gravity does not affect its horizontal velocity at all.
So
That is actually one of the three main ideas of today's lesson. Gravity only affects the vertical velocity. So you're never going to get to a point where even as it's going down, even if it's falling down really here, it's still, from this point right here to, I probably should have put it right here, it's still going to have that horizontal velocity. So I should have made it not so steep right there. It's going to look still kind of like that. And it's never going to get to the point where then it just starts to fall straight down. Now,
so it never will fall just straight down?
it'll never get to the point where it is falling straight down. Now, I say that theoretically we're ignoring the existence of wind resistance, okay?
Right.
Eventually the air pushing against it will stop it from continuing to move horizontally, and it'll essentially just be dropping vertically, okay? But even as soon as it rolls off the edge, okay? As soon as it rolls off the edge, I mean, there's only one thing acting on this ball.
And that's gravity.
That's gravity. So, in a sense, we'll find out, this is the second big idea, it's in free fall. It's in free fall, but it's also been kicked out this way a little bit, okay? So there's some things going on there. But let's just go ahead and cover all the different situations of projectile motion. That was close. So we have launched up, caught here, launched off horizontally, thrown down. Can y'all think of another situation? Throw it up, sure.
Move up.
By the way, these are all good pictures to draw on your notes. So if you haven't, I recommend that you do that. So, here we are with the ball, and we're going to throw it, and our friend over here is going to catch it. What does that trajectory, what does that path also look like? An arc, a parabola. So, yeah, everything is a parabola. Even if it's just part of a parabola. Well, we love this one over here, the original one, because it's the nice full parabola. But this one still is a parabola, that is to say it's parabolic, but it's just from what we would say the vertex onward. Same thing for this one, even if you throw it down, it's still from the vertex onward. This one is sort of a hybrid. The highest point is right here. But I could throw it in such a way, could throw this ball in such a way that maybe my friend catches it right at the highest point. So throw it up, and it's just about to start falling, and he catches it right there in midair. Okay? So still projectile motion. All right, this is not that mind-blowing, guys, but thanks for going and on. Okay? I could throw it, and it doesn't even get to its highest point. All right? maybe it just hits the wall. Yes, yes. See if I can go back over here. I have, in each of these situations, an arrow labeling the direction, or a vector rather, of its initial velocity. So here, it's kind of up and to the right. Here, it's completely horizontal. With this ball right here, the initial velocity, I'll put V naught, is down and to the right. Over here, we can see three different examples. This one up here has initial velocity. This one right here has initial velocity. And this one over here also has initial velocity. And we're noticing there, in all of these situations, when you first launch an object into projectile motion, that it has some initial velocity vector, okay, that I am imparting onto the object. And now all of our knowledge when it comes to vectors comes into play, where we actually can break that velocity vector, which has both an x and a y component, we can break it down into, we say, Vx naught, which is the horizontal part, or the horizontal component of the initial velocity, and Vy naught. I guess I can make this one, make it both solid, I guess. The vertical part of the initial velocity. Okay? I might have someone with some amazing athletic skills come up here with throwing. Do we have any baseball or softball players here?
I play softball.
Softball player, come on up, Jesus.
I'm kidding, I don't play softball.
No, I'm just kidding, you don't have amazing athletic skills, so.
Yeah.
Alright, so,
Let's go into the video.
alright, here you go. So this initial velocity is a vector. I'm just kidding. I kid because, at least when you're at the
Because you have a kid.
So, alright, I'm sorry, man, alright, okay. So, this initial velocity vector is like all vectors, and it has two pieces of information. What are those two pieces of information on a vector?
Direction and magnitude.
Not the x and y component,
Direction and magnitude.
the direction and magnitude. So we better put a, don't put a theta right there here. So just a little reminder, V naught has a magnitude and a direction. And to make sure that we're all aware, it's kind of speaking the same language here. Jesus, I want you just to throw the ball to me, okay? Let's just, if you can, maybe just, yeah, we're gonna try to have the same, almost the same exact throw every single time. So maybe underhand will make it a little bit easier since you're a softball player, okay? All right, so
Allegedly.
throw it to me underhand just a couple times. We're gonna try to be consistent here, okay? So just the same throw every single time, all right? Okay, great. All right, now, yeah, see what we're gonna do. Now here's what I want you to do. I want you to try to change the angle, and it doesn't have to get to me. Give me a regular throw, all right? Regular throw, underhand, regular throw. Okay? Now, I want you to change the angle, okay, of the initial velocity. Did y'all see that?
Whoa.
Okay? So, alright, regular throw again, regular throw. Oh, that was kind of a modified throw. So regular throw to me. Notice as it left his hand, if we were to do a little arrow, it would kind of look something kind of like that, right? Now, modify the angle, the way you did before. Boom. What would that vector look like? More up, okay? So the angle would be higher. So that would be sort of the difference between maybe your first throw had initial velocity like that, your second throw had initial velocity, something kind of like that, right? Okay. Give me a lesser angle for the initial velocity. Would y'all agree? Was that a lesser? I kind of felt like that was more of a less of a magnitude. You know what I'm saying? Give me the same magnitude, but just at a lower angle. Okay. Do y'all agree with that? See how you did kind of threw it a little bit, same force, but it's just a little bit lower. Now, regular throw, just so we can all get a frame of reference here. Regular throw, back and forth 2 times, keep going. Regular throw, here we go. Now, increase, same angle, increase magnitude. Not bad. Again, regular angle, so definitely a little bit higher there. And it came back to you. So, the difference there was between the regular throw with velocity and new throw, same angle, but a larger magnitude of the initial velocity. All right, y'all, does that make sense? And give me a lesser, so same angle, lesser magnitude. Yeah. Interesting, it kind of had the same result as when you had a higher angle. Okay, great. Dixie, let's round of applause here for initial velocity vector. Okay. So, I guess it would be good if we did a very short trig setup here. Velocity, initial velocity in the x direction is equal to, do y'all remember there was a little formula? What trig ratio would we normally use for the x part? Cosine. So remember, we could say that this initial velocity in the x direction, which kind of looks like hugs and kisses, but anyway, or kisses and hugs, is the initial velocity, so v naught cosine theta. If you need a little bit of a reminder why, well, that's because cosine of theta is that initial velocity, or sorry, Vx naught, the adjacent over the hypotenuse. And if you multiply both sides by Vx, or sorry, by, what am I doing here? Cosine theta is Vx naught over Vx, okay. So, yeah. There we go. That's what it is. And Vy naught, or Vo, okay? That's like it's like Vi, right? So,
Hillary Clinton.
all right, is V naught sine theta. That's money right there. Those two formulas.
Money. That's
Okay.
money.
Money in the grade bank.
Great bank.
Okay.
I'm broke there.
Funny because it's not true.
Wow.
That's why.
That's why I said it. He knows my physics grade. He said
It's a 0.
Okay.
still higher than yours.
All right. If we actually were to, let's see, if we were actually, I'm going to try my best to draw that big parabola, because that's the best situation.
Oh,
Okay?
you can hear me.
All right, well, the camera can hear all your whisperings too. Okay?
I was thinking about it. I was like, what am
So
I
just
back
watch
there?
out.
Y'all being kinky over there.
What are you talking about?
Watch your mouth.
Watch
All right, here
your
we go.
mouth.
That's not going in the video.
So, let's try to draw a parabola here, and not too circular-ish, but we'll try to draw it, okay? And we're going to pick some points. If I'm lucky, I'm going to get this to work out kind of the correct way. Try to make them equidistant. And of course, this side is steeper than the other, so it's not going to work out entirely as planned. Okay. So, there's some really interesting things going on here. You okay?
Yeah.
You check to make sure that everything's still in focus.
Yep, you're good.
Are we good?
Yes.
All right. So,
Hey, little mama, let me whisper in
here is the object's initial velocity. Here's Vx naught. And here's Vy naught. interesting thing here is, if I were to look at the velocity of it at this point, okay, from maybe each one of these is a different second. So after 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6, 7, and 8. If I did this right, so I almost did. Look at the horizontal velocity. I'm trying to make it, didn't really work out well. No, it's not, the slope is always 0, but that's not what I'm going for, okay? This horizontal velocity, I want you to think, this gets back to what Kim's question was a minute ago. On an object that's flying through the air horizontally, if we don't take into consideration air resistance, what is affecting its horizontal motion? No, gravity is affecting its vertical motion. The correct answer is nothing. Let me say that again. Nothing. Nothing is affecting its horizontal motion if there's no air. Kim, why is that a...
I just keep talking, you know.
Okay.
I'll ask
All right. If I had drawn this perfectly proper, what we would see is that this vector is the same length as this vector, is the same length as this, is the same length as this, which is the same length as this, which is the same length as this, and this. Okay? So the horizontal velocity is always the same. That's one of our 3 big ideas. The horizontal velocity, we can put this lots of different ways, is always the same. What's another way we could say is always the same, but maybe a little more technical?
Constant.
It's constant. So we'll say constant.
Constantly wondering if that class is really...
Okay, yeah, I'm gonna leave it there, yeah. Or at all of these different spots, the horizontal velocity is always what the horizontal velocity was initially. Okay? So let's say that this was, say, Jesus threw this ball at a speed of 2 meters per second. That means at this point right here, it's traveling 2 meters per second horizontally. At this point right here, it's traveling 2 meters per second horizontally, 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 and so on and so forth. All the way down to the end, even though here when I ran out of room, it doesn't really match very well. So that the horizontal velocity, Vx, is always equal to Vx naught. Like I said, that's one of the 3 big ideas. Here's big idea number 2. Let's look now at the vertical velocity. Okay, I'm going to try to draw that in red. Hopefully this one looks a little, well, black. So, horizontal velocity at that point looks like that. Horizontal velocity, looks a little bit shorter. A little bit shorter. Looks a little bit shorter, and then at that point right there it's 0. Then vertical velocity is going down. Then it's going down even more. Then it's even more negative. Then it's even more negative like that. Okay? Can you think of another situation that we've already talked about in our class, maybe not today, or maybe other previous days, of a situation where an object has a very large vertical velocity, then a little bit less, then a little bit less, then a little bit less, then 0, then it's negative a little bit, then it's negative a little bit more, then its velocity is even more negative, then its velocity is even more negative. Can you think of a situation? Free fall. Okay? In fact, if I were to graph the vertical velocity of this ball just going up and down like that, would it not look like this? vertical velocity very large, then a little bit shorter, then a little bit shorter, a little bit shorter, shorter. Eventually 0, it's going to come back down. I'm going to draw this over here off to the side. A little bit negative, a little bit more negative, even more negative, even more negative, and then very large negative. Do you see how these velocity vectors that are vertical match these velocity vectors that are also vertical? Does that make sense?
Oh, okay, that makes sense.
Okay. Jesus is coming up here, and we're going to try to create this arc again here, this parabola. All right. Throw it to me. All right, I'm trying to get that high. All right. We need someone coordinated. Mission, come on up here. You go. All right. At the same time that Jesus is going to throw that ball to me, okay? Mission, stand right here. I want you to try to throw this ball up about that same height, okay? So we can maybe kind of watch that ball over here. We can kind of watch it like this. Like, they'll go like this, and then like that. Y'all see what I'm saying? Okay, we're going to try to get it like that. I don't know if we're going to have this for this first time I've ever tried it here. Okay, so throw on 0. Ready? 3, 2, 1. Not too bad. Let's try that again. 3, 2, 1, throw. And we're shooting for a height about right about here, maybe. Okay? So 3, 2, 1, throw. Almost. 3, 2, 1, throw. Okay. I think we're doing pretty good, don't you? So y'all see what's going on, that vertically they're both doing the same kind of thing. Okay? This is kind of like stuff that we don't normally think about physics. Okay? We would think that it behaves differently. Great. Let's give a round of applause for these guys. Good job. Good job. Okay? So that's why I say that the vertical velocity and the horizontal velocity, they don't have anything to do with each other. They're just like two separate problems. Okay? So it's kind of like, so we've got horizontal velocity is constant. Okay? We could say that the vertical velocity, big idea here, spell it properly. The vertical velocity is like free fall.
Is that the second point?
That's the second big idea. Now, tell me some hidden information about free fall. A little bit louder? Yes, the acceleration, so I'm going to put acceleration in the y direction is always negative 9.8 meters per second squared. Now, this is something weird. When we now have something moving in 2 dimensions, in both the x and the y, well, you already realized this part. We have an initial, we've got velocity in the x, velocity in the y. We have acceleration in the x and acceleration in the y direction. But before you get too concerned and get a migraine over this, acceleration in the y is always what? Negative 9.8 meters per second squared. Acceleration in the x direction is always
0.
Why is it 0? Because the velocity is constant. It's not accelerating at all. Okay? So acceleration in the x direction is always 0. Okay? So that is why we can treat a projectile motion problem like a mashup, okay, of like a car problem traveling with no acceleration in one dimension, which is the easiest ever, like initial velocity and final velocity. Okay, they're the same. It's just going at 2 meters per second, 2 meters per second, 2 meters per second. Okay, that was pretty simple. It's a mashup between that type of problem, vertically or horizontally, and a free fall problem vertically. Okay, now I'm going to try. try this. Haven't done it in a little while. I'm gonna try to demonstrate this for you with this cart right here. So what we're gonna do, I'm gonna show you that the horizontal and vertical have nothing to do with each other.
Are those?
Alright, here we go.
No way.
Hold on to this one, will you guys? Thanks.
What? No way.